So, yes, I am Josh Bohde. I actually work at FG, and I make APIs and do NLP research. And you can find me on GitHub, IRC, and Twitter as that username right there. So, functional programming in Python. Python is actually not a functional language. It's actually a multi-paradigm language with object-oriented and imperative being like kind of its core paradigms. Functional programming in Python is always kind of foreign. If you've ever heard Guido talk about it, he doesn't actually like functional programming. He only will use it whenever it's better than like an alternative. But like Python has actually borrowed a lot of concepts from the functional world. Some of our beloved features, such as list comprehensions and iterators, directly come from the functional world. But because of the way functional programming is, all we really need is first-class functions, and we can do whatever you want with functional programming. And luckily, Python has that. If we can get into some theory here, if we had just a language with a bit of I/O and first-class functions, we can actually build up everything we would need to make it workable. So we could take, like, we could write booleans and conditionals, we can encode numbers and actually arithmetic with just the idea of functions. And this is why first-class functions are so powerful, because you don't need the rest of that to bootstrap a language. We're not going to do that because that's kind of crazy. We already have numbers and arithmetic. We don't need to write it ourselves. So like what first-class functions means is that you can use a function like you would any other variable. So we can rename it, where we renamed foo to Baz. We can put it in data structures, like when we put in a list, or we can actually pass it as arguments to other functions. So you've probably seen code like this, and there's duplication here. There's actually structural duplication if you look at it. The inside of the body of the for loop is the same, but if we just use like imperative tools, we can't really abstract this out and to remove this duplication. We can actually do it using object-oriented tools, but that would be like really, really heavy weight and actually destroy the usability of these functions. So we can actually use functional programming to make this a bit easier on us. This is known as reduce. So if we look back at those last two, we're going to need 3 parameters to our function. We're going to need like a base value and an operator, and we'll just make those arguments to reduce. And this allows us to just iterate over that list, apply that operation to the list, starting with that base value, and then return that. The canonical implementation is actually using recursion. But because of like the way Python works, we tend to avoid recursion if at all possible, because you're going to hit recursion limits after a while. And so by using reduce, our new definitions of like sum and product actually become one-liners. We'll need to like use the operator to find like the operators for add and multiplication. We'll still have the same nums in there, and then we'll just input the base values right at the end, and there's our sum and product. So Python actually does provide a little bit for like functional tools. It's got partial in the functools module. This allows us to, this is a higher order function, which means that it either takes a function or returns a function, and it allows you to partially apply the arguments to that function. So here, we're taking the function add, and we're partially applying 2. And we make a new function called add2. So whenever we call that function with a number, we just add 2 to its argument. This is really good as kind of like a base for whenever we need to like take a function that isn't quite how we want it and use it somewhere else. And then compose. Compose is something that Python actually doesn't provide for us, but it's really, really essential to how we start structuring functional programs. And it's pretty easy for us to write. What compose does is, in the base case, we have 2 functions, and we take the output of G, like in the code here, we take the output of G, and we make that the input of F. So we have a new function that is like composes F and G. But if we'd like to expand that to handle a variable number of arguments, we need to take this base case of 2 functions and abstract it out to a variable number. So if we go back to the product example, product is really, we multiply 2 numbers and get 1 number back. That was our cumulative function. Here, this is like a similar thing. When we compose 2 functions, we take 2 functions in and we get 1 function back. And we just apply that across. So we can define compose for multiple arguments by using reduce on our base case of composing 2. One thing you should notice is that compose is kind of, the logic will read right to left instead of the more common left to right. So in the add2 mult4 function, as the logic flows, we add 2 to whatever the input is, and then we multiply 4. This is a little counterintuitive, but that's just the way it's defined. So filter it's like reduce, and it works with lists, but it takes a predicate function and a list and will return a list of new values, a new list where the values for that predicate function are true. So it doesn't alter the underlying list at all. It just returns the values that pass the predicate. And then map takes a transformation function and a list and goes through that list and will actually transform each element of that list and provide you a new list with the transformed elements. What's really interesting about map is that this is probably the most popular of like the functional tools in Python because it's actually more of an interface instead of an implementation. So if you wanted this to be lazily done, itertools has an IMAP implementation for you. Or let's say I wanted to do these calculations, like my transformation function is like really, really heavy, so I want to do this in multiple processes. Multiprocessing actually has a pool class that has, I think, 4 different implementations of map that will distribute it amongst a number of processes. And the guarantees of this, you can actually like lighten them. For instance, like if you want to get them back as fast as possible, you can specify that you don't want ordering. And so you can actually, like, if you use multiprocessing.dummy, you can do this with threading. If you use like eventlet or gevent, they both have pool classes that do the same thing. So each of these functions aren't really too interesting themselves, but once we start to combine them, we get like a lot more interesting results. So if we had to write a sum of squares function and we had all of this already available to us, all we really need to provide is a function to square numbers, and then we can combine what we already have in order to form our sum of squares function. So, like the sum of squares, we'll take a list of numbers, then square each number and sum that. So we need a function that will take a list of numbers and square that to start with, starting from the bottom of the compose because it's backwards. So we'll use a partial to map the square over that list of numbers, and then the composition will take the output of that partial and put it into the sum, and then sum to give us the result. And you can see the results right there. So this is actually kind of bad because map produces an intermediary list. So that means with whatever list we have as input, we've actually doubled our memory requirements, and we've actually iterated twice for however many items we have. So this is probably way less efficient than what you would have written if you used a for loop. And this is where laziness starts to come into play. Python has laziness in the form of iterators and generators. You're probably really familiar with these. It's actually what powers anytime you use a for loop. That's just an iterator. So if you open a file and then iterate over it, it's just using the iterator protocol to not load the entire file into memory. It just loads it line by line. What you can do with iterators, though, is actually make them infinite, like this count generator here. We can just, count will just return 1 and 2 and 3, as long as you keep asking it for values. So it won't actually ever instantiate all those values until we ask it for it. So if I try to cast it to a list, we're going to run out of memory. Or if I try to add up all the numbers in an infinite generator, it's just going to spin until I either kill it or I guess I run out of memory because we hit an accent or something weird. So if we go back to the map and filter from before, we can actually implement IMAP and iFilter as lazy versions of those, just using Python's built-in generators. And this allows us to work with lists in a lazy way. So iFilter would take the list of counts and only filter it to be even objects. And then IMAP actually divides all those. So we basically have the same iterator at the beginning, except we're doing a whole bunch of calculation in order to get the same values. So when we call next on new counts, it asks the IMAP for its next value, which will ask iFilter for its next value, which will ask the original iterator for its next value, which will be 1. It'll discard that, and then it'll ask it again for its next value, which will be 2, which will pass, and then the IMAP will divide that by 2, giving us 1. So we can actually use this IMAP instead of map in that implementation of sum of squares to to not construct the intermediary list. So therefore, our sum of squares, we would only iterate over it once, and it would have a very similar memory and calculation profile as if you had written it using a for loop. If you want to actually play around with iterators in Python, the itertools module is great. It includes implementations of IMAP and iFilter and just tons of other things. And if you want to try to start working with iterators, they actually have an entire cookbook of how you can combine the functions in itertools in order to do really interesting things. For instance, here's a round robin implementation that just works for any iterator. So what functional programming in Python gets us is like two really big things, composition and simplicity. Composition in that our programs are actually just made up of smaller programs. We take these smaller functions and apply higher order functions to them, and then like compose those to get what we need. And simplicity in that our core functions, which we're providing to these higher order functions, are a lot smaller in scope than what we would have written otherwise. They take fewer arguments, or like their arguments are actually less complex. So one thing that you notice when you write functional Python is that the idea of a unit has become significantly smaller, because if I'm just going to square something, like there's the definition of it. I'm not working with like really large data structures or like complicated dictionaries, stuff like that usually. I'm pushing all that logic down into very simple functions. Since we like to test and we like to write unit tests, it seems kind of silly to start unit testing these. So I can always just test it for some known values. I can test that the square of 2 is 4 and the square root of 4 is 2. But that's just like basically a sanity check. I don't really have too many more values to test with this, because it's just writing lines of test at that point. Because we've actually started programming at a higher level abstraction, we should start thinking of how we can test at a higher level abstraction. And this is where something like Paycheck comes in, which is a third-party testing tool that you can just download off of Pippi. And what it will do is actually generate values for you to test declaratively. But because of this, because I don't know the input, I don't know the desired output, so I have to start thinking of what are the properties of my functions that I can test. So for the square root example, the math module has a square root implementation. So I could actually just test that my square root implementation works with the math module's implementation, because that's a reference implementation. But what we can also do is think about how these two functions relate to each other. So very roughly, like square and square root are inverses of each other if the argument is positive. So we can actually test this using Paycheck, and it will generate like a whole bunch of values that we wouldn't have tested ourselves. And because you can actually see the next screen, you'll see that this fails. And you probably should have expected this to fail if you know anything about floating points, because after a certain point, we're going to lose precision. So this is a property of our code that we've learned about that you probably wouldn't have learned through traditional testing methods. And we can actually decide whether we want to use this in our code, or maybe we can relax the test if we don't really care about, I think this is 20 places of precision. But it might be important, and so we need to rethink of the implementation of these functions to use something more like higher precision or whatever.
So that's failing because of the precision of the engine, not because of square root, right?
Yeah, mathematically, right. Square and square root should be inverses if it's positive.
So like you said, maybe we would need to round it first or something.
Yeah, or there's actually a decimal implementation. That would be a lot slower. It really, at this point, it depends on your application, but we know things that we might not have known otherwise.
Right.
Yes. And so really this is just a small sample of what you can do with functional programming in Python. There's loads of other things. So like I talked about laziness with lists. What happens when we have laziness with more interesting structures like trees? You can do really cool things with trees that are lazy. If you've ever written a parser before, definitely check out like parser combinators, which take combinators which are like kind of cool from a theoretical standpoint, and then make something that's really, really usable to generate parsers. And yeah, that's actually all I have for the talk. But I have some like live coding that I really hope is going to work. Yeah.
So is the function, you were giving like definitions of those functions?
Yes.
But are you saying, was that in that library? I missed what-
There's, the only thing that I used here that isn't provided is compose.
Okay.
Your tools can have most of that stuff.
Yeah. But it's also really heavily biased towards working with iterables. When you're doing functional programming, like there are things you need to compose and do things with functions that aren't in the context of iterables. This is where like Python only really cares about functional programming when it comes to iterables. But there's other things you can do with it.
So compose is the one you said was right.
Yes.
You could just define it.
Yeah. And I actually almost always do that. So I just, I define pipeline like a Unix pipeline, and then reverse the arguments and pass it to compose. Okay, so in 1986, Knuth was actually asked to write an article on literate programming. And he was given this task. You're supposed to read a file of text, determine the n most frequently used words, print out the sorted list of these words along with their frequencies. His resulting implementation in his version of Pascal that is literate was 12 pages long and had bugs in it. And actually Douglas McIlroy sat opposite him in this article and reviewed the code. He actually talked about how like clever Knuth's data structures were, pointed out the bugs, and then proceeded to write a 6-line implementation using the Unix shell. So I'm actually going to recreate this program because McIlroy's actual implementation is functional. And the resulting Python is actually very similar to what you would do in the shell. So we know we're going to have to use text. So I'm going to import read. I need to extract words out. And based upon Knuth's original implementation, it's just alphabetical characters. It doesn't account for hyphens or commas, whatever you might have. So word read equals read.compile. A-B, A-Z, A-C, plus. And then, so we're going to.
I think we lost you.
What?
Yeah, we lost you.
Is there any way you could use like a light background theme? This is pretty hard to read.
Yeah.
Assuming you can get it working again.
Let's see what first thing says. Did anything? No.
No.
Maybe over here it died? No?
Just. Oh.
Okay, back in. Back in. That's. Is that
There we
right?
go.
That has the weirdest wrapping. It totally doesn't look like that. So like, let's def a words function that will take, so we're gonna be working with files here. We know that a file is an iterable of lines. We only care about a line, and then we'll do words read.split line, and we need to return value in there. So, like right away, this doesn't work because split actually takes delimiters, and so I need to inverse that regular expression. And let's assert words. This is a line equals this is a line. And run it in IPython. Words read is not defined. Word. Okay, so we got an assertion error. I don't actually know what that is. So we can run this and see what the value is. So we got like a weird trailing empty space.
I think we lost you.
Yeah.
You lost me again? We're service.
It's like,
Yeah.
keep like moving.
Oh, I gotta keep moving this.
It's like your last line is cut off.
Yeah, everything is like totally cut off. Should we go back in main? Yeah. And like the shortest buffer. So there's like that weird trailing line space. So we need to get rid of that. That's from Pivot Tools, import iFilter. We just need to filter that out basically. I definitely know there's a way using regexes to only get the matching stuff, but I would pretty much have to pull up the docs because it relies on match objects and stuff, and I can never remember their API. So iFilter, bool, then we'll send it over. So, go. We'll cast that to the list.
I think we lost you.
Lost me, didn't I?
No, never mind. Still there.
Is it
Never
the screensaver?
We got you.
Okay.
We got you. Yeah. We're good.
Oops. No. There we go. So I can just send this over. It'll run all my assertions. It'll evaluate the entire buffer. So we have words now. We need to split out the words in a file. So let's say like def words file. We need a file name. And then return words. We need to map this over. So we need to imap words over the file, which is opened. And then let's words file main.py. Let's test that. There we go. So we actually get all of the words in a file now. Per line. we need a way of like counting these now. So word counts will equal compose. So if you've ever used, like, there's the counter class in collections. This works brilliantly for this. It's what you would call like a multi-set in like another language. Collections or counter.
Yeah, we lost you again.
Here we go.
You're back.
There we go.
Counter. So words in a file. So this isn't quite the right shape. So like words in a file returns an iterator of iterators. We just want one iterator. So this is, why does, is there, do you guys see a C there?
Mm-hmm.
Chain. So, like this is part of the boilerplate when you're working in functional programming. We need to transform that iterator of iterators into an iterator of just the words. So, chain that from iterable will actually do this for us. This is one of the things you'll find in like the IterTools cookbook. They call it flatten. It just takes an iterable and returns an iterable containing all the elements of each iterable in that iterable. If I explain that well, I probably did. Then so we can send this over. And word counts pi. So this is what a counter looks like. It's very similar to a dictionary. And so we can start getting like the counts off of this. So we need like the inmost common. I don't know. So we need to like modify our word counts function for that to accept an n. Return. So we already have a counter. And then, so this will give us a counter back. What a counter does, it actually has stuff from the heapify or the heap module to get the most common elements off of it. So it has the method most common. And it has the file name. So let's get the two most. So then we have like the two most common words in the file name.py is now line and words. So that's pretty much it. Like one thing you'll notice is that like I really rely heavily on like IPython to do my like checking, which is something you don't really see in like traditional Python development. Like if you're working in like Django or something like that, you're gonna just like do a run server and like refresh the page all the time. When you have stuff that's really simple like this, it's a lot easier to just run it in the shell and get like immediate feedback, which shortens the dev cycle and allows you to check the logic like a lot quicker than like hopping over your browser and refreshing the page.